New large language model made for science. This is such a good idea. We are going to be adapting models for specific domains. They can be so much better if you adapt them, for example, for science. Intern S1 is an open source AI model designed specifically for scientific research. Think of it as a super smart assistant that can understand text, images, molecular structures, time series data like earthquake waves. Most AI models today are great at popular tasks like chatting or basic math, but struggle with specialized scientific problems. Intern S1 bridges this gap. So let's check the architecture. This is very interesting to me because I have my own LLM architecture and I wanna try to improve it and make it train better, faster, stronger. And I'm gonna maybe re-implement this LLM and pre-train it maybe. So it's using mixture of experts, 241 billion total parameters, a lot of parameters, 28 billion active parameters. Usually my LLM would have like million here, these numbers but million. And then each of the experts actually can be actual expert in chemistry, physics, etc. So it has three key components: vision encoder, so it's gonna be vision transformer, converts images into 256 tokens, digestible pieces for the AI, dynamic tokenizer, this is one of the most innovative parts, traditional tokenizer, same for everything, so if we have text is equal to water is H2O, their tokenizer, dynamic tokenizer, will adapt to content type. So for chemistry, it's gonna tokenize H2O differently or specially, as opposed to water is. Chemistry formulas, like these ones, need different processing than regular text. Model achieves 70% better compression for scientific data. This is so interesting, I like this, we can learn so much from this. This is what you need to do for LLMs. Time series encoder handles sequential data, earthquake readings, heartbeat monitors, compresses long sequences into manageable representations. That's so interesting. Let's look at the training process, the teaching of the model. We have pre-training, this is learning fundamentals, 5 trillion tokens of data. They have a lot of compute, I can see. 2.5 trillion tokens of scientific content, that's very interesting. PDF research papers, web data filtered for quality. We can do this actually, by the way, but I just don't know how. Somebody needs to give me compute. We need to figure out how to get all this amount of compute. They have this smart PDF processing pipeline. So PDF document splits into pages, check for equation symbols, simple pages, low cost parser fast, complex pages, high cost parser, accurate but slow, merge all pages, clean scientific text. I don't know if they released this, but I wish they released all of this. Then we have post-training, fine-tuning skills, offline reinforcement learning, and by the way, I want to do all of this, it's so interesting. Offline reinforcement learning. The model practices on curated question-answer pairs. Best answers are selected from multiple attempts. So I think this is just without model generating and trying to answer. It's just giving it questions and answers and using reinforcement learning. And online is model trying to answer and then seeing if it answers correctly, you reward it. So that's the difference, I think. We have math problems that are programmatically checked, easy to verify. Creative writing, we need AI judge for that. So math, chemistry, check if answer is correct, binary. Writing dialogue, use AI to judge quality, nuanced. What makes it special for science? Domain-specific understanding, mathematics equations. So it's just been trained on this data, that's what it means. Chemical structure, so they just somehow created this data. Protein sequences, physics formulas. We can do this. This is not so difficult. We just change. Here I have model I trained on medical data. We just need to create this data, which is not too difficult. Any programmer can do it. They show these benchmark scores, but I don't know if that's too important. Benchmarks are not gonna, they're so tiny part of like just answering some questions, but science is a lot more about just knowing like some textbook exam questions, A, B, C, D or whatever. But this is the best thing we can do for now, I guess. So we got good chemistry results, material sciences, molecular tasks. But this dynamic tokenization, I think, is really important. So tokenization adapted for science. So if we have equations, if we have chemistry formulas, we need to have different tokenizers. This is so cool. We can use Cloud Code or Coding AI to create this PDF parsing. We can also run a model, OCR models, like a Vision LLM, to look at the PDFs and then just write. Here you have synthetic data. Oh my god, I have so many ideas for this. Performance on scientific tasks above Grok 4 Gemini Pro, which makes sense because this is how powerful custom training is, and we're gonna do that on our channel as well. And I think Grok 4 is doing this as well, so Grok 4 is gonna be crazy soon. Sorry, Grok 5 I should say. And it's possible to generate synthetic data by looking at the real data, rephrasing it, creating a few more examples based on this real data, a few different examples, and then using automatic checkers for what you can as well. And you can train on that. And that's gonna be maybe the next big thing, like reasoning, the synthetic data. They also have dynamic resolution for images. If image is complex, resolution is dynamic, can be 400 something or higher. So if it's fixed, then 256 tokens per image, but if it's dynamic, it can be more, depending on the resolution scale. These images are gonna get into this amount of tokens, but complex scientific diagrams, higher resolution, they're gonna do it in higher resolution and more tokens. Then we have this time series data, like seismic data, these are numbers, or we have EEG readings or astronomical light curves. So we have solution to be adaptive downsampling. So from a long vector, we create small vector. I'm guessing this is a neural network. Or it can also be programmatic. So I think it can be both. Not sure which one they use though. For example, if you have 1 billion samples per second, you can just take one sample per day. I guess you need to take representative samples. So either if your data can be taken automatically or programmatically, then you can, or if you need a neural network, maybe for some type of data, you can build that as well. Training data, the secret sauce. Instead of treating all web pages the same, Intern S1 groups them by website. Example, chemistry.org website, sample 100 pages, LLM analyzes patterns, decision for entire domain, I guess entire 100 pages, keep all, if they're high quality, rewrite, this is kind of synthetic data, or discard if it's low quality. So rewrite if information is good but poorly formatted. There are some people outside chopping some wood, they're a bit loud. Why this works? Websites have consistent quality or formatting. One decision affects thousands of pages, much more efficient than page-by-page analysis. So they do it for entire website. The scientific data recall pipeline. Problem: scientific content is only 2% of web data. That's actually more than I expected. Smart filtering increased it to 50%. They trained some AI models to classify, recognize this data as scientific. So archive papers, Nature article, and some out of domain. So different format but same content. So research paper, textbooks, examples, for example. They use teacher, big expensive model that's very accurate, and then distill that into student, and then process a lot of data, entire internet of data with that. So they're just gonna keep scientific content and discard other content, like medical study, biology research, math tutorial, etc. They can also include some general educational content kept as relevant because it can actually teach the model to understand scientific stuff better as well. They don't use one classifier for all sciences, they use 6 specialized: mathematics, physics, chemistry, life sciences like biology, earth sciences, materials. It's not just about filtering out bad content, but also finding scattered good content. If there is a lot of life sciences content, they're gonna just keep the best content, but if material sciences doesn't have so much content, then they're gonna be more lenient or flexible. General tip: small batch size is good early in the training because model doesn't know how to what to do, where to go with the gradients. So a lot of iterations will quickly teach it. Iterations compound on each other because the smarter model is, the better it's able to reduce loss. So a lot of small batches is good when it doesn't know anything, but it's gonna converge slower because small batch size, it's just gonna converge slower later when it knows where to go. And opposite for the large batch size. Solution is to schedule a batch size, start small, 4 million batch size, and then scale to 10 million after 400 billion tokens, for example. So this is visual example. FBA training, I'm still trying to figure this out. So they have this special handling of mixture of experts plus FBA training. They have some other interesting things. This is just filtering data. And then they have, that's it.